Well, thank you, Bradley, for that introduction. Thanks to the whole program committee for inviting me. It really is a pleasure to be back in Amsterdam at this time after all these years. As it said in the call for papers, and as Bradley said, here's the book that David Garlan and I wrote 30 years ago, and happy birthday, book. So the idea is to talk now about software architecture, starting in the past and working up through the present, and everybody wants to talk about AI, so I'll talk also about the AI futures and what that means for us and what we can mean for it. I'm going to talk about, I'm going to talk historically. I'll say a little about the origins, in which we had expected a bigger image there. Okay. We have system-level abstractions that matter, and realizing that there are system-level abstractions was the first big key. I'll talk about the maturation, which followed a kind of normal process, and I think it's important to kind of walk through and understand that normal process. I'll say a little bit about the evolution, but not a whole lot, because I haven't actually been working in software architecture for 10 or 15 years. And then what everyone wants to talk about is the AI-induced future. So at the outset, way back in the dark ages, there were some conceptual foundations that got us started. There was information hiding, programming in the large, Unix pipes and filters. These are pieces of history that you may recall. And as time passed, we went from information hiding through abstract data types to objects, and there came a time at which everybody was talking about how objects are going to solve all our problems, which has a flavor kind of like AI is going to solve all our problems. But I kept realizing that there were problems that objects weren't going to solve. I mean, you could cast them as objects, but it wasn't very helpful. And so I started thinking about other things that we know and love that have the same kind of organization as objects do, and keying on the de Raymer and Krohn programming in the small and programming in the large paper, which kind of turned us around from thinking about programs to thinking about collections of programs. Now, the language that they devised was a provides and requires language and didn't make distinctions among different types of components. But when you start thinking about the limitations of objects, and even just thinking about objects compared to pipes and filters, which were, you know, over in the Unix world, that's what they think about, you start seeing different patterns. And looking for patterns is one of the ways we find interesting research. So we move on from there to say, well, we've got objects and we've got pipes and filters. Are there other kind of canonical program organizations that we know and love? And when do we reach for them? And how can we understand their innards? So we went from architectural abstractions to, let's see if that helps. We began in the late 1980s, early 1990s, thinking about different kinds of program organizations we can know and love, and then driven by the model of machine descriptions that Bell and Newell had in their computer organizations, started looking at different types of components and different ways that they interacted with each other. I mean, yeah, it's procedure calls underneath, but what are you trying to accomplish with the procedure calls? What abstraction are you looking for? I'll come back to that point when I talk about AI. But the essential insight here was that developers have a shared folklore of common useful patterns, and if you can tease out the folklore and get it organized, you'll be better off. So I think overall, there's a way to think about progress in software development and programming languages. And that is, you know, every field likes a chart that goes upward to the right, because upward to the right means progress. And for me, the mark of going upward to the right is how big is the conceptual chunk that you don't look inside of? You know, is it fetch from memory and store, or is it some enormous framework that gives you thousands of lines of machine code for invoking a very small abstraction. And this isn't history. This is impressionistic. Don't put too much faith in the location of any particular thing. But you'll see that software architecture is sitting there in the kind of late 80s to early 90s as another way of thinking about software development, and is a bigger chunk from its predecessors. But we've gone on from there, and there are other things. You know, we've got frameworks, we've got IDEs, and now we have the prospect of AI generating code for us. Now, there's one note that I will make on this chart, and that is that up until the present, pretty much every place along the line, you could trust the underlying processor to translate properly the things you said into the underlying code. That's another point I may come back to. So the main ideas that came out of that were component-level abstractions and different types of components, not just features in programming languages. The connector, the interaction between two components as an important abstraction. That there are distinct types of components, distinct types of connectors, and there's some type checking rules. You can't do arbitrary choices. You've got to match appropriately. That there are some architectural styles that we know and love, and that we can have visual and textual languages for doing this, and libraries that go along with them. So that's the prehistory. Now, to talk about the maturation, I want to refer back to a paper that Redwine and Riddle wrote. It was an ICSA test of time paper, if I remember correctly. And they looked at the way technologies mature in software. This was a long time ago, and their technologies are obsolete, but I think the overall scheme they laid out is a good one, and a good one for us to understand. So as you start with basic research, and there's some key idea that leads you into investing a little bit more in concept formation. As the concepts get clearer, more people come to the party and start working on various aspects of the concept. You do development and extension. It then becomes big enough that you can start using it on projects of your own. And at some point, you've learned enough, built enough tooling, and built enough confidence that other people may start trying it out. And eventually, it may become, if it is successful, it will reach popularization. So I want to go quickly through the stages that I think software architecture touched on along that path. Not so much because all of you care about the details of that history, as because it's a good example of the way a technology matures, and it should affect the way that we think about how we position the research that we're doing and the development that we're doing, and the way we test out the ideas and transfer them into practice. So software architecture started off with some underlying conceptual roots, and followed a path kind of like this. This is the Redwine and Riddle bits laid out on a very approximate timeline. Our foundations, as I indicated earlier, were things like information hiding, abstract data types, objects, layered systems, and so forth. And these are all concepts of their own. They had their own cycles of 20, 30 years. They continue on their own paths. But these are some of the things that we stood on when we got started. I think our basic research period was from the 70s into the 90s, where we got the basic models and the basic plans. We had product line architectures well before we were really talking about architectures. And we had those in particular domains. For example, avionics. Garland did a big study of oscilloscopes in the early 90s, for example. Missile control was doing this. We had catalogs of common idioms, not so much architectural is, you do it this way, you do it that way. We had at that point object-oriented programming techniques working through the object-oriented architectures. We got UML for better or for worse. And the main idea here was that there was a shared structure and a shared vocabulary, and that we'd benefit by teasing these ideas out into the open where we could see them and talk about them and compare them. The concept formation period was one of elaborating these basic models, and that ran through the early 90s. Here we had better abstractions for system structures, for component interactions. This is where the idea of the component as a particular entity and a particular typed entity, that we could recognize different types and what they were good for. That's when that emerged. Some early formalization, some taxonomies and views, and this is when we saw the first institutional support for the discipline in the form of workshops and the very early books. Like our book. Then beginning in the mid-1990s, we had a period of development and extension, and here was a period of unification of the ideas and refinement of details and second generation concepts. So we got some architecture description language. The patterns community was forming just over 30 years ago, actually, and in the patterns community, there was also a lot of interest in the patterns that lead to architectures. We saw issues about interoperability and some refinement of the technology and some conference tracks, and the first WICSA was 1999, before we dropped the W. Then there was a period of internal exploration where people were trying it out on their own systems, giving explicit attention to architecture and design, and talking about quality attributes, not just functionality, but other things that we care about. This was a period in which they were called non-functional attributes. Over my objections, I really wanted to call them extra functional attributes. But we seem to have settled on quality attributes, and that's okay. We had some formalization of designs, some analysis and exploration, and then a number of books on practice, and you can start seeing software architecture in book titles in about this period. External exploration brought us UML, the rational unified process as an industrialization using the Kruchten 4+1 views. Object-oriented frameworks, component-based software engineering. So you can see the spread of the idea that you should be thinking about components interacting at the system level during the first decade of this century, roughly. And the key, I think, to saying that this is a real winner was that in 2010, CNN Money said software architect was the best title in the United States. That's some sign of having arrived. And then from then, we get a period of popularization with production quality components, with engineering ideas. We have architectural patterns that are fueled by the web, and frameworks. We started getting architecture standards at this point, and the architect was not just a fancy title. It became not just about the architecture of the system, but the title of the senior technical leader, who really had the overview and the insight into what the system was about and why it was the way it was. Courses made their way into the curriculum, and then we got conferences not only for research but also for practice. Okay, so why did I just spend however much time walking through 8 slides full of ancient history? I mean, sure, that's interesting history, but what I think is important for people today is to understand that technology goes through these stages. And unlike some of our colleagues who think that all research ought to be directly transferable to industry, I think there's an important thing going on here in filtering and refinement. So not every flashy new idea is going to work out. And At each stage of this cascade, you're willing to invest a little bit more in a little bit bigger project to find out what it might do. So the key concepts in basic research, those projects are of a scale that you can run in an individual lab with half a dozen people. And as you go down the cascade, it takes more and more investment. And when you start doing it in production products, you're putting your product at risk. And so having gone through a stage in which bad ideas get dropped out because they don't pass the filters, that is valuable insulation for the actual production side of software. So I really think it's important to understand that this kind of cascade, maybe not this set of details, but this set of opportunities to try it out and try it out with greater risk and try it out with still greater risk, and then try it out with confidence in something that actually matters to the company. It's important to understand that this is happening and to understand where you're sitting in this line and what you have to do to move to the next. You know, I said yesterday during the discussion session that the research community has a bad habit of writing individual little papers about what I did last semester and piling them up. There are pernicious external forces that drive us to do this, but they also dissuade us from taking that pile of papers and turning it into something bigger that would be more appropriate at the next stage down the line. And one of the reasons that I think that the research community needs to spend more time unifying the individual ideas is because it just isn't fair to throw a bunch of individual papers over the wall and expect somebody who's trying to do real work to use them. There's a joint responsibility to figure out how to unify and refine the ideas so that they become useful farther down the technology chain. Okay, so the maturation of software architecture for localized systems ran through a path like that. It's a pretty common path, and I don't think there's anything especially important about the details, but understanding what the path is, I think, is important. That set the stage for addressing bigger kinds of systems, and I'll talk about a couple of them. Heterogeneous distributed systems and systems for specific domains. And I was not doing architecture research at about this time, and so what I'm reporting on is the experience of two of my collaborators from a paper from the mid-90s who have continued to work in architectural domains. We had occasion to review this and write it up about a year ago. So I'm going to pick two domains for examples, and I'm sure you know about others, but this is how we move on from the original ideas of architecture, which are about single systems that you can hold on to and you can own, into to larger systems. So my own expectation was not realized. When I started out working on software architecture, I knew, like all of you know, that when you write down a description like this, it becomes documentation and it becomes obsolete almost instantly. And so my expectation was that we would have architecture description languages where the description of the system that you were building was in a language that was compilable. That is, that there would be some super version of make that would take your description, find all the code for the components, generate a lot of the automatic code like turning procedure calls into RPCs, and that would be the definitive version of the system, and if it wasn't correct, the build would break. And that's not how it worked out. So I got fooled. We went someplace else. We wound up at a point where frameworks and development environments and corporate workflows and corporate commitment to having some kind of uniformity across the company in the software, that dominated individual architectural choices per project. And so the point that we wound up with is where the architecture is implicit in the development system that you choose. And regret this a little bit because I still think that you ought to be able to look at a project and say, what's the right architecture for this project? But I also understand, and we heard this yesterday morning, that the thing that you're doing fits into a bigger system, and it has to integrate with that system, and if it doesn't integrate with that system, then you may be just great, but you're breaking something else. And so I understand that tension, and that's where we wound up. So one of the things that has happened in the intervening years from 2010 or 15 till now is that a great deal of architecture support has become domain-specific and embedded in the particular tools that go with that domain. So, you know, software development is a lot about managing conceptual complexity. And if you bury the conceptual complexity in the infrastructure, then people don't trip over it as much. And in addition to that, when you bury a lot of that conceptual detail in the infrastructure, then people who are not highly trained professional software developers can develop software. That is, vernacular programmers, vernacular developers can take control of their own software rather than relying on the vastly fewer highly trained developers. The number of people developing software for themselves because it's incidental to things they're trying to do, the ones I call vernacular developers, they outnumber us by an order of magnitude, right? There aren't enough of us to serve all of their needs. And so for us to embed the knowledge about doing it well into tools that they can use gives them leverage. So we're doing some of that. And one of the things that my collaborators have pointed out is that a lot of the architectural ideas have become constructs in languages. Data flow and Apache Beam give you Unix pipes, except Unix pipes on steroids. They do the work for you. And then domain-specific ecosystems handle the plumbing. And just to make that concrete, there's more to it than just code. So Stack Overflow does a survey every year and asks people what they're using. The most recent one that I can find is actually a few years old, but this is a snippet of their map of systems that people are using. This is the snippet that is related to web development. And you'll see that software development here is resting on an ecosystem that has not just programming languages, but also databases, frameworks, IDEs, languages, platforms, connected in myriad ways. And so the place we have got to is that there is an ecosystem architecture that is much more than the architecture of the software system. It's not just about the code anymore. So back to domain-specific software architecture support. We've got ecosystems like that. And browsing through the program for today's conference, I see reports on domain-specific architectures in microservices, digital twins, cloud deployment, and several reference architectures. So this is where we have come to. A second example is about heterogeneous, highly distributed systems. When I was doing research in software architecture, we had components and connectors, and the software developer could identify them and pick them and talk about hooking them up. But with big heterogeneous distributed systems, the connectors are no longer local and they're no longer locally owned. My collaborator says that TCP IP addressing hinders clean abstractions for naming and semantics, and that moving to the cloud requires reconciling different protocols in different subsystems, that he is coping with the need to integrate systems from different places and different companies, and that there's no natural, simple way to do this. And a lot of what he has to do is to think about the way to bridge those communication gaps. And what he'd love to see is connectivity abstractions for modeling. And again, in this conference, there are papers on distributed systems, on edge computing, microservices, and cloud-native operations that seem to me that they must be dealing with just this sort of problem. Okay, now we can come to the AI-infused future. Where are we going from here, and why are we going there? So we hear a lot about how software engineering is going to be devoured by AI. AI is going to make all of the programmers obsolete. AI is going to make all the software engineers obsolete. AI is going to let us narrate what we want and then just go off in a corner and produce it for us, and everyone will be happy. Well, I'm not sold on this. I think software engineering is alive and well. That software engineering covers all aspects of software, not just producing computer code. And I think it's worth looking at the long-term relationship between software engineering and AI, in which we've had one and we've been successful. I think software engineering is going to evolve to handle LLMs and generative AI. And the principle that I take into this is one about automation. I believe about automation that what you ought to automate is stuff you already understand. You ought to automate things that are well understood, and in particular things that are tedious and error-prone when you hand them to humans. You hand off the detail work to automation, and currently that means AI, right? But you reserve the conceptual work and the intent for humans. So we have now tools that are good at doing detail, and so we can talk about the what. But the theme of this next segment is the why. That AI is really struggling with understanding the why things are the way they are. So let's see, in this audience, I do not have to explain that software engineering is more than computer programming. At this point of discussion, I sometimes have to go into this excursion, but I know I don't have to do this here. I do think it's worth talking about engineering, because we're not, software engineering researchers are not always clear about engineering. Software engineering is a rich and robust discipline. We cover systems through their lifetime. And I spent once a sabbatical reading history of engineering and found, lots of different definitions of engineering, but they all boil down to about the same thing. And this is the recasting of that definition for software. That software engineering creates practical and cost-effective solutions to computing and information processing problems, applying the best systematized knowledge available, developing software in the service of mankind. And that service of mankind phrase doesn't always show up in people's definition of engineering, but it's almost always there in the engineering disciplines, discipline of engineering, and I will argue that it belongs here. There's a difference between software engineering and classical engineering, like civil engineering and chemical engineering and mechanical engineering. And that is that software engineering is design intensive with small manufacturing costs. And I have seen over the years unfortunate outcomes from making inappropriate mappings between stages of software development and stages of manufacturing automobiles based on the amount of time that goes into it. Software engineering is design intensive. When you're developing software, you are not doing the production, you are developing the tooling and the jigs that would be used for the production. And our production runs used to be pressing CDs and putting them in shrink wrap boxes, and it's now distributing it over the web, probably automatically without notifying the user that you're doing it. Our discipline is design intensive. And unlike traditional engineering, our material is symbolic and it's abstract, and it's more constrained by intellectual complexity than it is by physics. So those are differences between software engineering and classical engineering. But I believe that the argument about classical engineering, the definition of classical engineering, the intent still applies. It's about understanding what the client needs. It's understanding the trade-offs that are context dependent, depending on what the client actually wants. And an absolute commitment to finding the most cost-effective solution for the client. That is an engineering approach, and that is absolutely appropriate to software engineering. Okay, now AI. Software and AI go back a long time. I remember when Lisp was turned loose in the world, and those of us who were programming on 709s with 32K, not G, not M, K, 32K of 36-bit words. We looked at Lisp and said, oh my God, they're throwing away half of memory for pointing at what comes next. How can that be a good use of the machine? Right? Well, we received this as a gift from the AI folks. We now use linked lists regularly, and I think we've mostly forgotten where they came from. That's just part of our data structures course, not a gift from the artificial intelligence folks. I think this is the kind of pattern that we've had with AI over the years, that we get some kind of love bomb from AI. We say, oh my God, can we cope with that? And then we say, well, we could use it for this and we could use it for that and we could understand it in this way, and then we absorb it into the way we do business and we forget it came from AI. It happened with programming constructs like linked lists and functional programming. Everybody know that functional programming was a gift from AI, not our own programming language people? No? Yeah. Design approaches, heuristic approaches are very much AI approaches. Working with partial solutions, refining partial solutions toward acceptability, exploratory programming, that's a gift from AI. Conceptual shift from we compute with numbers to we compute with symbols, very much an AI gift. As we come to grips with specifications being not really practical in many situations, we are learning to deal with complex, ill-structured problems, and indeed one of the original names for the field that we call AI was complex information systems. So we don't need to be scared of AI. We've dealt with them before. We know how to make treaties with them. They give us new concepts. We incorporate them. We forget where they came from. So don't panic. LLMs and generative AI. Okay, that's the new disruptive idea that we've received from AI. What do we do about it? Well, there are a lot of particular panic points that people have. We have complex models over huge data sets. They allow predictions of outputs, but it's limited to inference from prior existing data. It's programming by mimicry. It's how can I deliver? How can the AI deliver something that resembles things it's seen before in the context that seems to be there in the prompt? Those results are predictions from prior traces, prior things that have been captured in some way, and inferences from those. And what we're getting is predictions. There is no semantics there. Right? There's no intent. There's predictive replication of similarity. If you're looking for that, it ought to look. I'll give you something that looks like something that I've seen before. And that's okay, because a great deal of what we do really is similarity. Remember transactional databases? when we were predicting the cost and effort of development, I freaked out over function points because anyone remember function points? Yeah, okay. The function point effort predictor says look at the specification, look at all the things that are asked for, and there are, 2 or 3 grades of difficulty, and then just add up the points, and that's your prediction. And I looked at that and said, a specification that says obey the laws of physics, and also when you see this signal turn the green light on, those are not the same amount of effort. Well, sure enough, they're not, but function points worked really well in relational databases. And relational databases are the bread and butter of predicting that the thing is going to look like the last one, because adding a new transaction to a relational database is just like adding the last transaction to a relational database. That's the kind of thing that AI is going to be helpful with, rather than inventing and conceptualizing new things. Anyway, their properties of concern include things like data size. Well, we've dealt with terabytes of data before. We've dealt with complex structured data before. The opacity of the reasoning. You get a third-party software component, and you kind of believe that if you had the source code, you could read the source code and figure out what it did. But in practice, it's opaque. We've dealt with practical opacity, even if we didn't really believe it was opaque. We've had non-determinism ever since we have had software that controlled physical objects. The non-determinism in AI is different, but it's not like non-determinism is foreign to us. And so the properties that people are concerned about have analogs in software engineering. Software engineering can evolve from the analogs to deal with the AI versions of the same thing. It's not something we need to freak out over. I will say that speed and scale remain challenging, and that's one of the issues that I've heard here in the last day. But I think the real issue for us is that software has relied on our roots in formal symbolic reasoning. Even if we know we can't prove something, we still have this itch to write down a specification and show that it really is correct, even though in practice it usually doesn't happen. And that rigorous symbolic reasoning is fundamentally different from statistical prediction. And I think the big thing that we should be thinking about as we're doing all the particular things that we're working on is understanding how we can come to deal with probabilistic reasoning rather than rigorous symbolic reasoning. That shift, I think, is the fundamental one that we should be working on. So what about the AI stuff? Software engineering relies heavily on implicit and tacit knowledge. In yesterday's keynote, Louis Brin decided ways that his customers sometimes learn to depend on things that they weren't supposed to know about. There were bugs in the system, but you couldn't fix the bugs because the customers had compensated elsewhere, and then when you fixed the bug, there were double compensations, and that was a bad thing. And that information about who is doing what to whom just flowed around through the oral history as far as I could tell from the presentation. I also mentioned customer use of hidden data objects. And if you don't know that the customer is using the data object, you don't know that you have to be backward compatible. Software engineering has to deal with unrecognized assumptions. One of the pieces of our canon is the paper we call the Wicked Problems paper. The paper by Riddle and Weber from the planning community, actually, from the 1960s. And the point of that paper is that when you're dealing with a computer system that is embedded in a societal setting, that the stakeholders are diverse, they have different objectives, they are inarticulate about their objectives, and they are sometimes intentionally inarticulate about their objectives because their real objectives are not socially acceptable and they have to hide them as something else. So there's knowledge in the client that is not in the hands of the developer. And understanding how to navigate that is the reason that we still read the Wicked Problems paper. There's domain knowledge as well that may not be well documented. There are software decisions that are often they're tacit. We don't use that tool this way. Why not? Well, we don't because if you do, then something bad happens over there. But it's not written down as part of the training set. It's a piece of oral history that you just know that gets transmitted informally. And since much of the expertise is not available in explicit text, it's not available to the training sets. And if it's not available to the training set, then it's not available to shape the actions of the AI system. So to drive that home, in Plato, there is an allegory of the cave. You all know Plato's allegory of the cave, right? Yeah, right. In Plato's allegory of the cave, the short form is that there's a collection of people who are constrained to see only shadows that are cast by other objects. And their entire knowledge of the world is driven by what they see in those shadows. And because that's all they ever know, they mistake the shadows for reality, whereas outside the cave, there's a real reality in which things, do the things that shadows don't. I will say that the LLMs are trained on the shadows. So here's an example of a 3D projection. It's a puzzle that goes around, and you've probably seen the puzzle in one form or another. It says, think of an object that casts a shadow of a triangle in one direction, a rectangle in another direction, and a circle in another direction. And here is a depiction of such a thing. Well, what you get out of that is an object. And when I first encountered this puzzle, the object wasn't a thing that was 3D printed to look like it was wood, but it was actually a paper cup. So it used to be that drinking fountains had a paper cup dispenser where they'd dispense a little flat paper cup and you'd push on the edges and it would turn into something that would last long enough to drink the water. And by golly, it was circular at the top, it was rectangular in cross-section because that's how it was packaged for the dispenser, and when you opened it up, it was triangular. So if you only see the shadows, you won't see the detail about how it is turned into a cup. And furthermore, you won't see a lot of the context that goes with it. So this particular version of the cup can be folded out of a single sheet of paper. That's an interesting piece of context. And in addition, this particular version was developed something over a century ago in a tuberculosis sanatorium for the purpose of improving hygiene because the cups were disposable and they wouldn't get shared. Okay. Now, none of that you would get from looking at those three shadows. And so I say the AI systems are trained on the shadows, and there's much context that doesn't come with them, and that context often matters. Nevertheless, there's a lot that AI can contribute to software engineering. One is raising the level of abstraction in programming, and here I will remind you of this picture. AI is pushing us farther up into the right. And as I said earlier, one of the things that's a little troubling right now, a lot troubling right now, is that at all previous stages you could trust the translation. And in the current state of AI technology, you cannot completely trust the translation. But we still can have AI-based development tools. The AI tools are really good for detailed work. You can do checklists, you can do conformity checking, you can remember to check all of the boxes, not just the boxes that you got checked before quitting time. And this is particularly true for vernacular programmers who don't really know what boxes they should be checking. But you get less help with high-level design. And it is at the architecture level and above that there is so much embedded knowledge that is not written down that you really do have to rely on human judgment. So that is how AI can help with SE. And how can software engineers help with AI? Well, there are going to be new software architectures. The incorporation of AI-based components and the management of those components in which you're doing model refreshes on a different kind of cycle than you are for conventional software. We have a lot to say to AI about how to organize systems so that you can manage them through the future. AI is going to bring us new kinds of components, and we can help to formulate them as components that can interact with other components. Integrating LLMs will challenge us for new system architectures. And the general statistical unpredictable nature of Gen AI calls for new adaptations. This is the guardrails discussion. How do we put in checks and balances? But we have built software out of unreliable components before. I think that higher level concerns like ours are not threatened. Requirements in design and reliability, they're hard to automate because they're highly context dependent. They depend on a lot of tacit knowledge. And they demand judgment and common sense and sensitivity. Engineering says we need to try to produce what the client actually needs, and a lot of that is something that it takes human judgment to pull out. We'll get help with checking case analysis, suggestions, things for us to think about, but under careful supervision. AI may help us navigate complex design spaces, again, because of the ability to manage detail. My bottom line is that AI can generate options, but that we as engineers have to navigate the trade-offs for a particular client setting. Okay, what about correctness? Software engineering has a really complicated relationship with correctness. Beginning in 1968, when Bob Floyd told us you can write assertions about programs and prove them, we started following the line. We have this conviction in our minds that we ought to be able to write a full specification and a proof. And as I said earlier, that's in tension with engineering, where we don't have enough knowledge to actually write that specification and the proof. But we still have this fixation that we ought to be able to do that. It's kind of wired in. And you say, well, no, you can't. Yeah, I know, I can't actually do it, but I really want to. So we've inherited that from computer science. And we know that doesn't match practice. And we know that we need to satisfy. We need to do something that is good enough. We need to get the best cost-effective solution, not the perfect solution. And I am thinking that software engineering needs to come to terms with this tension between our fixation on correctness and our obligation to be cost-effective. And that we should be thinking about success as being the result is fit for its purpose. It's fit for its purpose in the context of the purpose. And that is good enough. And we should be cheering when we get it good enough if we haven't cheated on thinking what good enough is. And so a challenge for any project is figuring out what good enough is, and then figuring out whether what you've got is good enough. So I've you may have seen this picture before, but to try to crystallize what good enough means, I've laid out some examples along two axes. One is how terrible is it if it goes wrong, from who cares to catastrophe. And the other is what's the degree of automation, or what's the chance that an actual human being will notice and intervene before something goes terribly wrong. And I've got, nuclear safety devices in the upper corner where they're automated, but you really, really, really don't want something to go wrong because the results are catastrophic. And down in this corner, I've got, finding a restaurant for dinner tonight with a free app that you downloaded from who knows where. If it leads you astray, then okay, so much for your dinner, but this is not that big a deal in the grand scheme of things. And I've laid out a lot of other examples along the way. And so this is an example of how to think about how good you have to be, when is good enough. And also a little bit of warning about mission creep. IRS 1040 there is the US tax form. And the original computer support was just letting you fill things in, and you're doing the arithmetic on your own and the interpretation of what you could deduct on your own. Then we get applications. One of them is called TurboTax that tries to do a lot of this for you. Now you've got more automation, and consequences of getting the taxes wrong are kind of middling. It's more than I didn't see the right movie last night, but it's not as bad as I went bankrupt. But now you care a little more about whether TurboTax is doing the right thing, because it's doing things that make interpretations that maybe you didn't. Maybe you could be more creative and save money on your taxes. Oh, in the United States, tax avoidance is okay. It is looking for interpretations that let you pay less tax. That's fair game. It's tax evasion, lying on your tax forms, that's not okay. And so that gets involved there in when TurboTax starts automating it for you, are you getting all the advantages that you might otherwise get? Similarly, in the 1970s, automotive cruise control sensed how fast you were going, let you set how fast you wanted to go, and then decided how much to push on the accelerator. But it didn't slow down if there was something ahead of you. It didn't have access to the brakes, and so it didn't slow you down if you started rolling down a hill. And so you had to pay attention as a driver. It was just relieving you of maintaining the right speed on the highway. Well, that's not where cruise control is anymore. And so there's been an enormous amount of mission creep from the 1970s to now. And the warning here is that when you have an application, you need to attend to how it's being used, because the demand for fitness for task, the demand for reliability, the lack of oversight, that may be increasing without you quite noticing. So pay attention, please. I've talked about what I think are the limitations of LLMs and generative AI. It's that you're dealing with statistical likelihood, not with validated semantics. It kind of works out because humans are pretty regular in the things that they do. The automated bug fixing software is relying on you having said something similar someplace else in the program that they can copy over into the offending location. So we do a lot of things in systematic, repeatable, regular ways, and it's absolutely appropriate to reuse those rather than reinventing them. But remember that similarity in phrasing is not a substitute for accuracy. You still have to do checking on it. And the LLM training sets don't have access to tacit knowledge. And so we're still after fitness for purpose, we're after good enough, but we still need to be careful about supervising the systems to see that they're producing good enough. Okay, so that's the tour. I started out looking at the origins. I talked about the maturation cycle and why it matters, even if the details, our details don't. I talked about how software architecture has evolved since I stopped actively working. And I offered some opinions about an AI-infused future. My hopes for the future is for us to make progress by seeking conceptual patterns, looking for regularities, and then finding ways to exploit those regularities, and to get new and more powerful abstractions by reflection on the things that we have done and the things that we see. That's how I got into software architecture. That, I think, is one of the ways that I generate good research problems. Is to see what is the regularity that I am seeing here? Is there a way to generalize? And so I see opportunities like using AI to generate useful new abstractions, about getting abstractions right for highly complex distributed systems, about definitions of useful design spaces, which is one of the ways of organizing what you know to find the regularities, of finding abstractions that are genuinely useful for vernacular programmers and don't mislead them into believing they have built something that's safe and reliable, or just because they haven't asked about it, because they didn't know to ask about it. To try to be more explicit about the design obligations that go with our tools, the things that are part of the underground culture, the hidden knowledge, the corporate knowledge, to try to tease those out to make them more accessible to our tools. So that's where I've been, and that's where I'm going, and thank you for listening.